In this lecture here, we want to move into section 2.4 and expand on the topics from the previous section where we learned about linear functions and slope by talking a little bit more about slope, diving deeper into the concepts. So we have three main objectives we're going to cover in this lecture here. The first thing we're going to do is we're going to find the slopes and equations of parallel and perpendicular lines. Then we're going to, real briefly at the end, that's going to take most of this lecture, and then we're going to talk about how you interpret slope as a rate of change. And in that instance there, what I'll do is I'll work an application problem. And then at the end, I'm going to talk about a function's average rate of change. Okay, so first off, we'll talk about parallel and perpendicular lines by beginning with parallel lines. So this is how you can tell two lines are parallel. So if two non-vertical lines are parallel, then they have the same slope. Okay, so what that means, two lines are parallel if, and I'm going to denote it like this, M1, the slope of the first line, is the same as the slope of the second line. Okay, so this is just so we're clear here. M1 is equal to slope of line 1, and M2 is equal to slope of line 2. Okay, and then the reverse is also true. So if two distinct non-vertical lines have the same slope, then they are parallel. So if you say, oh, okay, look at these two lines, their slopes are the same, they're parallel. Okay, I reference non-vertical lines here. So vertical lines as a kind of a tangent here, or number 3 here. Vertical lines, two vertical lines are parallel. Okay, and the reason you could say that is you can't really compare their slopes because vertical line slopes are undefined. But when you were to graph any two vertical lines, you can see that they are parallel to each other. So here's line 1, and then here's line 2. All right, so this is the key concept here when dealing with parallel lines. This is the key concept here. And so what I want to do now is I want to give you some information and use that to find the equations of lines that are parallel to other lines. All right, so here would be the first example. So write an equation of a line that passes through the point negative 2 comma 5 and parallel. So I'm telling you it's parallel to this equation. Okay. So just recall, what do you need to find the equation of a line? So to find the equation of a line, first thing you need is a point. Okay, we got that. This is great. So I've got the point. And the second thing you need is the slope, right? So all I'm telling you is, look, it's parallel to this line, to this equation right here. Y is equal to 3x plus 2. Well, we know parallel lines have the same slope, okay? So the line, since I'm saying it's parallel to this, the line I'm looking for has the same slope. All right, so now I could just use the point slope formulas, right? So y minus y1 is equal to m times x minus x1. So this over here is my x1 comma y1. So this is y minus 5 is equal to 3 times x minus 2. And then look, you can see here, y minus 5, distribute 3x. Negative becomes a positive, so 3 times 2 gives me plus 6. And then I'm going to add 5 to each side. So you get y is equal to 3x plus 11. And look, this is what we're saying. Okay, this line right here is parallel to this line, and that's true because look, they have the same slope. They have the same slope 3. But this line here just goes through this point right here. And you know, if you were to graph these two lines, this is just a rough sketch of what these graphs would look like, okay? This might be the y is equal to 3x plus 1. And then if you were to graph this, it'd be way up here. And you could just see that they're parallel. All right, let's do another one. All right, so let's write this one's got fractions. Okay, write an equation of a line that passing through the point 1/3 comma negative 1/2 and parallel to the line whose equation is y is equal to negative 2x plus 1. Okay, so look, we got the point. It's 1/3 comma minus 1/2. And look, we got the slope actually too. The slope here, you can see, is the same as this line because I'm saying it's parallel to it, so it's -2. So good. Right off the bat, we got the point, we got the slope. Just use the point slope formula. Y minus y1 is equal to m times x minus x1. So this is my y. So this is y minus 1/2 is equal to -2 times x minus x1, which is 1/3. Okay, so now you're just going to have to work with fractions here, right? So this is y plus 1/2, because minus minus becomes positive, is equal to -2x, and then minus minus becomes plus 2/3. Well, all you're going to have to do now is subtract 1/2. So these cancel out. And I'm going to move this over here just so you can see the fraction. So I got 2/3 minus 1/2. The LCD here is 6. So this would be 4/6 minus 3/6. That just gets me 1/6. Just like that. And look, same slope, -2, just different y-intercept here. All right, so parallel lines, pretty straightforward. Okay, now perpendicular lines here. So if two non-vertical lines are perpendicular, then the product of their slopes is -1. Okay, so first of all, what do perpendicular lines look like? You know, what this means is if you were to sketch one, this would be line 1. Line 2 might be, a perpendicular line might look like this. So what it means is it crosses it to form 4 90-degree angles. And we'll say slope of line 1, we'll call that m sub 1. And again, slope of line 2 is equal to m2. So what this is saying is, look, these two lines are perpendicular. If you take m1 times m2, and you get -1. Okay? So then also it's this, kind of the reverse too. If the product of those two slopes is -1s, then those lines have to be perpendicular. And a horizontal line having 0 slope is perpendicular to a vertical line. So if you look here, all horizontal and vertical lines are perpendicular to each other. Excuse me. Here's a horizontal line, and then here's a vertical line. They will be perpendicular to each other. Okay, but this right here, this is the key feature. And we're going to use this right here to help us find the equation of perpendicular lines, okay? All right, so let's just do a bunch of examples here. All right, so let's find the equation of the line perpendicular to y is equal to 3x minus 12 and goes through the point 2, 3. All right, so again, you need a point. Well, we've got that. We're saying the line I'm looking for goes through the point 2, 3. But what I need is the slope. And all I know is they're perpendicular. So when I do this, when I take m1 times m2, it's got to be equal to -1. All right, well look, this right here is my m1, okay? This is the slope I'm given. So the perpendicular line is going to be slope m2. So I'm going to replace 3 times m2 is equal to -1. And then I'm just going to divide both sides by 3. And look, slope of m2 is equal to -1/3. Okay. There's another way to handle this too, is if you're given, you know, one slope here, you can just see that m2 is always going to be equal to -1 over m1, meaning perpendicular lines are the negative reciprocals of each other. All right, but here, look, now we've got the slope, m2, and we've got the point. So use the point slope. So it's y minus y1 is equal to m times x minus x1. So this is going to be y minus 3 is equal to -1/3 times x minus 2. So distribute here. So y minus 3 is equal to minus 1/3 x. Negative negative becomes plus 2/3. And then I'm going to add 3 to each side. Well, 3 is the same thing as 9 over 3. So I'm just putting over common denominators here so you can see. So this is minus 1/3 x. 2 plus 9 plus 11/3. And so look, perpendicular lines, their slope is 3. It's the negative reciprocal of 3 is negative 1/3. So these two lines are perpendicular to each other. All right, let's do another one here. Find the equation of a line perpendicular to y is equal to minus 1/2 x minus 2 and goes through the point 5, 9. All right, so again, you got the point. What you need to do is find the slope, though. But I know they're perpendicular. So when you multiply the slopes, they got to be negative 1. So I got negative 1/2 here times m2 has got to be equal to negative 1. So really what you can do is you could multiply both sides by negative 2. Negative 2 times negative 1/2, that's just 1, so those cancel out. And look, negative 1 times negative 2 is 2. And look, you can think about this. The slopes, what I'm saying here, hinting as the slope of the perpendicular line it's the negative reciprocal, so it's minus 1 over minus 1/2. Well, negative negative is a positive. Keep, change, flip. It's just 2. So this is y minus y1 is equal to m times x minus x1. Here's my point. So this is y minus 9. My slope is 2 is equal to 2 times x minus 5. So this is y minus 9 is equal to 2x minus 10. And then when you add 9 to each side, you get y is equal to 2x minus 1. And look, their slopes are negative reciprocals of each other. And when you take 2 and multiply it by negative 1/2, you get negative 1. So these lines are perpendicular to each other. All right, let's move on to two quick final topics here, talking about slope as the rate of change. And slope is defined as the ratio of the change in y to the corresponding change in x. So basically it describes how fast y is changing with respect to x. So for a linear function, okay, so the straight line function, slope may be interpreted as the rate of change of the dependent variable per unit change in the independent variable. So the dependent variable is the y and x. So it's just telling you, look, how much on average does y change per unit, all right, when you change the independent variable x. It's just the rate of change. And I'll show you an example here, okay? And this data is pretty old, but we'll go with it. In 1990, 9 million adult men in the United States lived alone. So look here, you have two variables here, okay? So we're going to think about this as ordered pairs. So my independent variable here is going to be the 1990, the year. So think about that as my x. And the dependent variable here is going to be the number of men who live alone. So I'm grouping this as an ordered pair. Now in 2008, this number had gone up and 14.7 million adult men in the United States lived alone. Okay? So let's use this information to find the slope of the linear function representing adult men living alone in the United States. Let's express the slope correct to 2 decimal places, and let's describe what it means. All right, so I'm going to take this other set of data here, and I'm going to have that be my other point. So if you were to just treat these as ordered pairs, you can compute the slope here. And I'm not going to go through it in much detail here, but you can see the slope worked out here. Into 2 decimal places, the slope between these ordered pairs is 0.32. All right, and so what this is the rate of change here. Okay, so the slope here is the rate of change. And what this rate of change is telling us is, look, how much does the y variable change? Okay, and the y variable here is men living alone. okay? And this is when x changes, okay? And this is going back, all right, how much it changes per unit change in the independent variable. Well, the per unit here is per year. I was just going to give the rate of change, okay, and x variable here is per year. And so what this positive slope telling us is the number of men living alone increased, because it's positive, at a rate of 0.32 million men per year. So that's what I mean by the per year. Okay, so the rate of change is, it looks like it's going up, 320,000 basically, or 0.32 million men per year were living alone. Okay. Let's end now talking about the average rate of change of a function. So the slope here, okay, is the rate of change for a linear function, okay? But so what would the rate of change be for any function? So any function that might not be the function that is nonlinear. So let's let x1 comma f of x1 and x2 comma f of x2 be distinct points on the graph of a function f. Well, then the average rate of change of f as you go from x1 to x2, all right, is the following. You take f of x2 minus f of x1, so that's kind of the change in y, right? Divided by x2 minus x1. So it's still the same thing. Still the slope formula. All right, so let me do an example here, and then I'll try to explain it for you. Okay. Find the average rate of change of f of x is equal to x cubed, okay, from x1 is equal to -2 to x2, which is equal to 0. All right, so let me just real briefly show you what this graph looks like, okay? So we know it's a cubic, right? So a cubic is going to look like this. So I want to find the average rate of change when x is -2 to here, to x is equal to 0. So what you're going to do here is just follow the formula. It's going to be f of x2 minus f of x1, with going back, divided by x2 minus x1. Okay, so this is going to be f of 0 minus f of -2 all over 0 minus -2. Well, look, f of 0, when I plug 0 into this, okay, when I plug 0 into this, it's going to be 0 minus. When I plug -2, -2 cubed gets me -8. Divided by negative becomes a +2. 0, negative becomes a positive, so 0 plus 8 is 8 over 2, which is 4. So really what's going on here is, look, this graph is changing. It's a polynomial function. But if you were to draw a straight line between those 2 points, okay, here and here, the slope of that line would be 4. And that's what it's saying is, look, the average rate of change, it's the rate of change here of the cubic, it's not constant, but the average rate of change across from -2 to 0, all right, is 4. Now, if you were to pick 2 different x values, you'd get a different rate of change, okay? Unless you picked 0 and 2, you'd actually get the same. But otherwise, if you were to pick, like, find the average rate of change from 1 to 7, you would get a different value. All right, so for this, just follow the formula. Think of slope as rate of change, and follow the procedures for finding parallel and perpendicular lines.